Hello. We've run out of letters. We hit the end of our bounded buffer of alphabet, so we've got to wrap around. This will be video AA, and it even feels kind of like we're starting all over with the topic we're looking at, pointers. They're not going to feel like they have anything to do with object-oriented programming. They're pretty low-level bits and bytes and hexadecimal numbers and all that. So that puts the burden on me. I'm going to have to convince you that, yeah, we do need to know about pointers for object-oriented programming, and I'll see if I can fix you right up. First, though, I'm going to start with a walk down memory lane and do a recollection. Recall a variable in memory where else would it be? Well, yeah, that is a little redundant. A variable in memory has two values associated with it. Two values associated with it. Why am I claiming this is a recollection rather than brand new stuff? Because we had to look at this when we were doing reference parameters to functions. Remember that? Ah, yes, it all comes back to you. One thing is the value itself, and the other thing is the address. And I'm going to do an example, go along with that. My variable is going to be my counter. Not terribly interesting. But let's say my counter currently has value 12, and I will label it as such. Value. It's got a variable name, but here's the deal. I don't even know if I should go there, but I'll go there. By the time your program's translated to machine language, my counter is long gone. Your variable is represented entirely by its address. So the addresses are really important. The other piece here is the address of where this variable lives in memory, which I'm going to make up a value, hexadecimal 1020. That is just as arbitrary as the 12 I put as the value. I just made that up. I said, let's pretend that this variable called myCounter lives at address hexadecimal 1020 in memory. This is the address. But wait, there's more. In addition to being called an address, this is actually called a pointer value. The address, also known as, aka, a pointer value. So we're sneaking up on what pointers are here. A pointer value is the address of a memory location. In this case, particularly, the address of variable myCounter. The hexadecimal 1020 is called a pointer value. And I'm going to put a working definition down here of that. Definition. A pointer value is the address of the memory location. Full stop. That's it. Is the address of the memory location. Memlock for short. M for memory, LOC for location. That way I fit it on just 2 lines. Another definition. Definition. The one that's going to be increasingly important to us. A pointer variable. P-O-I-N-T-E-R. Variable. Now let's pause and think about that for just a second. Well, let's see. A pointer value is the address of a memory location. We're always going to see those specified in hexadecimal because that's how the machine's looking at them. Shorthand for binary. A pointer variable holds a pointer value. Okay? Now, with my picture drawing convention, that actually is pretty easy to illustrate. That is pointing with this arrow to this variable. This address right here, that indicates or points at where that variable lives in memory. At least it makes sense to me. Let's look at syntax of pointed variables. Meaning, how do we do that in C++? Whoa, that green doesn't want to erase. Apply with it. I'm going to call this, you know what, I'm going to do my comments in green, if I can find a green that works. I may not be able to. I can't. I'll use blue. That'll mix it up. Blue for comments. Pointer variable syntax. And away we go. Int, this is probably somewhere near the top of your program, maybe near the top of a function, and away we go. StarP, semicolon. We've seen integer variables before. We know the variable naming syntax conventions. What's new here? Well, I'll use my blue for comments. What's new here is this means P is not just a garden variety integer variable. P is a data type. This is actually the two-piece data type. Data type. Pointer dash to dash int. Pointer to integer. I'm calling it a two-piece data type because int by itself is not the data type. The star all by itself certainly is not a data type. But int star is a data type pointer to integer. What we're doing is telling the compiler P is not going to hold a simple integer value like -5 or +13 or whatever. It's going to hold some wild and crazy hexadecimal number that's the address of something in memory that we're interested in for whatever reason. Now, keep going. Pay attention to the black stuff for the code. Int, and I think the variable is my counter. Is that right? My counter. Semicolon. That is a plain old garden variety variable. And you know what? I'll stick with what the picture I had. I shouldn't have erased it, but I don't have much room. My counter. It had value 12, I believe, and lived in hexadecimal 1020 or 2010, something like that. So here's variable my counter. I'll go ahead and set it to 12. Why not? There. I can initialize that to 12 for what it's worth. Where's some new stuff? Here's some new stuff. P equals, and oh no, I hate this. Almost as hard working in C++ as the star is the ampersand. The ampersand means something different just about for every context you could possibly type it in. I'll stop talking and start writing. P equals ampersand my counter. Now I said I was caught up to where I was. I accidentally did not tell the truth. Here's variable P. Variable P springs into existence when we hit this line that says int star P. It makes a variable P. It's initially garbage. I didn't initialize it to anything. Even though P is going to hold the address, it also is a variable and has its very own address in memory. I can make up any address I want. What address do I want to make up? I don't know. Hexadecimal 2250. No significance to that. It's just got to be a different address in my counter because those are two separate variables. Pause and let the computer try to reconnect. Okay, so P has its very own address because it is a variable. It's a type pointer to integer. Someday it will point at some integer memory location. At the moment it points at nothing. It's random garbage. And my counter, I've got that all cut up. All that was set up for this right here. P equals the address of my counter. And I'm going to put the little bracket down here to do the explaining. I would read this, read as the address of my counter. The ampersand there means don't get the value of the variable as the value of the right-hand side of that assignment. Get where it lives. The single ampersand in this context does not mean a reference. We're not talking reference parameters anymore. This means the address of whatever follows it. The address of my counter is, according to pretend land up here, hexadecimal 1020. So the value of the expression on the right is hexadecimal 1020, and that becomes the new value of P. So P is no longer garbage. It's now hexadecimal 1020. And a good habit that I recommend getting into right away is when you're working with pointer variables, illustrate where they point at. Draw a picture to get this solid in your mind. This point's right there. And that's how it's described. Variable P points at variable my counter. Variable P points at memory location 1020. That's the value of variable P. I know it's a little bit confusing, and I apologize. This hexadecimal number up here, that represents where P variable itself lives in memory. This hexadecimal value down here, that's the value of P, but it's the address of where somebody else lives in memory. That's the connection. Okay. So, that's not much, but that's a little, so I'm going to hit a cout statement here. Cout, less than, double quote, star P colon, close double quote, less than, star P, or asterisk P, your choice, less than, double quote, space, my counter, and I think I want to put a colon after my counter. I'm going to have to continue the cout on the next line. Cout, less than, and my counter. So much longer cout statement than I had anticipated. And that'll be it, inline. Now then, cout, star P, my counter. Let's see if we can predict what the output of that will be. Output. Well, it's almost like a competition. The ampersand. I'm the hardest working symbol in C++. The asterisk will fight back. No, it's me. Yet again, the asterisk means something different. This right here. It's going to print out verbatim. We don't have to worry about that yet. It prints out verbatim the star, the P, the colon, the space. All that is just a quoted string. This, the way I would read this, the way I do read this, is all messed up. What's pointed at by? How many prepositions can I string together? Pointed at by P. The star in that context is called the indirection operator. We don't want to print out the value of P. We don't want to see this nasty hexadecimal number. We want to see what's stored in the memory location that's pointed at by P. So let me read this back. Print out the string verbatim. Star P colon space. Now then, don't print out P. You actually can print out P. You would see a wild and crazy hexadecimal number that would be hexadecimal 1020 or something looks a lot worse. We either get that or this way. Read what's pointed at by P, because P, a star in this context is the indirection operator. Go to what P points at, take that value and print it out. So what's pointed at by P, follow the arrow, is a 12. All of that just to get a 12. And then I didn't leave space. My counter is also going to be 12. I don't know what I did with my array. Oh, here it is. So we printed out exactly the same 12. We printed out the contents of the memory location twice. One of them we did it with our eyes wide open, and one of them we kind of snuck up on it. This is indirectly, maybe that's why they call it the indirection operator. This is indirectly going to where the 12 lives and printing out the 12 right here. Star P colon, then go to what's pointed at by P, print out the value, we get the 12. This one is the eyes wide open. My counter colon prints that out. My counter, yeah, I know I'm printing out variable my counter and it's 12. No mystery there. Okay? Now, the output's in the way. I'm not quite sure how I'm going to do this. I've been writing bigly, and I need to reclaim some board space. So how am I going to do this? I hope you've got this written down. It's going away. And I'm going to do board wraparound. I've just gotten wraparound crazy lately, have I not? There. Now, anything that goes off the bottom of the board, I can wrap it around and put it up at the top. I reclaimed some space, so I don't have to do that just yet. StarP equals 25. Semicolon. Nothing brand new in that statement, thank goodness, mercifully. But it's still something new from the previous statement. What's pointed at by P? This. Let me read this out loud the way I read it to myself. My own explanations to myself. 25 is the value of the right-hand side of that assignment. That's not hard to do. The left-hand one is a little tricky. Take the 25, don't put it in variable P. Don't wipe out the hexadecimal 1020. Take the 25 and put it at what's pointed at by P. 25, put it at what's pointed at by P. We have snuck in the back door and changed the value of variable myCounter. We knew where it lived, and we could go there and give it a new value if we wanted to, and that's exactly what happened here. Now, I'm going to get real lazy. I'm going to stay real lazy, and I'm going to say ditto, and put in parentheses, same cout statement. You might want to pause the video and take time to just write it again, because now I want to see what the output is now that I've done this relatively innocent looking little assignment statement here. But watch what happens. The output, StarP, verbatim, colon space, what's pointed at by P? What's pointed at by P is now 25. I just now set it to 25. No great mystery there. Here's the mysterious part. myCounter, colon, turn out the value of myCounter. The value of myCounter is 25. Even though I had no assignment statement that said myCounter equals this new thing. I snuck in the back door and changed the value of myCounter without variable myCounter even knowing about it. It doesn't even know what hit it. Let that sink in. If it will. Okay, wrap around, dot, 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 coming in from above. You think that's crazy? Watch this. P equals new. When you type in new in your editor, it's going to change a special color. New is a reserved word in C++. New what? New int. I'm using blue for comments. This, the new, that's actually an operator. It's sort of like a function call. You call the function, I'm going to even call it a function. You call function new, it runs out there and finds some storage that your program's not using yet. In this case, just the right size to hold an integer, stakes its claim, says this now belongs to the program that I'm working on behalf of, and it returns the address. That was quite a mouthful, I know. Let me get some stuff written. This is the dynamic, N-A-M-I-C, dynamic memory allocator. It's probably O-R, I don't know. Dynamic memory allocator. What does a dynamic memory allocator do? Grabs, good computer word, grabs a fresh, this is very loosely stated, grabs a fresh chunk of memory marks it as being used and returns its address. See me describing it like a function? That's not only a mouthful, that is a brainful. Let me read that back. P equals new int. The word new all by itself is the dynamic memory allocator operator. What a long name for a short word. here's what it does. It grabs a fresh chunk of storage of memory that's not currently being used by your program. It doesn't belong to a variable. It's not part of the machine code of your instructions. It's a brand new chunk of storage that your program's not using. It marks it now as being used. Maybe you could think of it as competing with other programs that are currently running in memory. Oh, I want that memory, I want that memory. This one is going to grab a chunk for you, for your program, mark it as being used, and then send back its address, which is going to land in variable P. So this is wraparound, by the way. This is after we've already done these statements down here. Now we do this one, coming in from the top. Watch what happens. The right-hand side, let's evaluate the right-hand side. The right-hand side says, find me a new chunk of storage. Oh, I don't know, where am I going to find a new chunk of storage? Oh, way down here in the corner. I found a new chunk of storage at hexadecimal F014. Again, I made that up. This is absolutely positively going to be garbage when we first grab that chunk of memory. That's the value of the right-hand side. Not only did it find this chunk that's just the right size to hold an integer, that's why we have to specify the data type after new to tell the dynamic memory allocator how much storage we want for this variable. And then it sends back or returns, think of it that way, it returns this hexadecimal value of where this new chunk of storage lives in memory, and we're storing it in variable P. So the hexadecimal 1020 is now overwritten with hexadecimal F014. Not only that, I've got to update my picture. That means that variable P, our pointer variable, does not point at my counter anymore. It's now pointing at this weird, strange, nameless variable down here. We can hereafter, because of the star operator, we can treat this storage as if it's a variable, but it doesn't have a name. A nameless variable. Strange stuff. Well, let me use it that way. I hope you got this blue definition down. I am really not using workspace very wisely, but I hope this still makes sense. So right after that, let's do the StarP thing again. StarP equals, see, I used 25. Let me use 178. Why not? Now let me read this carefully with all the blue Dr. English euphemisms down here for how to read these things out loud. The right-hand side, 178, that's easy. Where are we putting the 178? We're putting the 178 at what's pointed at by, I erased that, what's pointed at by P. We're not giving P a new value. This gave P a new value. This gave P a value that is the address of a chunk of storage that we asked for. We are explicitly asking for new storage for our program here. The address got stored in variable P. This is now using that storage that we just now got. This says don't put 178 in variable P. We just worked so hard to get that new address of storage. Put 178 in what's pointed at by P. Now I know I'm repeating myself. Put it with what's pointed at by P. Here's what's pointed at by P. P has value F014 that points at this memory location, and that's where we put the 178. So, I'm going to, I guess, wave my hands again. I don't want to eat up all the little board space I have, so I'm going to say same cout statement. That's the only cout statement I'm using right now. What will that same cout statement, which is this one right here, I left it on the board, at least I had enough foresight for that. The same cout statement, what it's going to produce as output, this will be my little output area down here. I'll separate it from everything else. The output. It prints out StarP, colon, and a space. Then, say it along with me. What's pointed at by P? What's pointed at by P is 178. Then space, the string my counter, a colon and a space, and the value variable my counter. Now look what happened. P doesn't point at my counter anymore, so when we changed what's pointed at by P, it had no effect on the value of my counter. So my counter is still 25. Lots of strange stuff going on here. This might be a video you might want to watch more than once. Now, that is a big mess. But you've got to be able to draw the picture. I've got to be able to draw the picture. This is not stuff I try to keep in my head. When I'm writing code or reading code where pointers are involved, I've got to have scratch work where I draw pictures. That goes with the territory. Okay, one more piece, and then I'm going to close off this discussion and hope that sinks in some. This is storage. It's like, what is it? It's the rough country cousin of a local variable inside a function. Local variables inside functions are called storage class automatic. That just means they magically appear when you call the function. They magically disappear when the function hits the closing curly bracket and the local variable falls out of scope. Terminology flying around all over the place, good grief. That's a local variable in a function. This one is a cousin. This is a dynamically allocated variable, storage class dynamic. You don't get storage for what's pointed at by P until you ask for it. Give me that chunk of storage. Well, there's a flip side to that. It doesn't automatically go away. When you're done with one of these chunks of storage that you explicitly ask for, you have to tell the system, okay, I'm done with it. Delete. Delete P. And I'm going to put a comment on that one because, I don't know, could very well be one of those top 5 errors. Delete P releases, R-E-L-E-A-S-E-S, storage pointed at by P. Why did I say that funny and make a big deal and write a comment and everything? Here's the misconception that we have to get past. This does not get rid of variable P. Variable P, I erased it, but variable P lives as long as the main program or whoever defined it. It is a variable in its own right, just like my counter is a variable. So you cannot, inside the program, say, well, I'm done using variable P, make it go away. What you have to do, though, is if P holds the address of storage that you explicitly asked for, then you have to tell the system when you're done using that chunk of storage, and this is how you do it. Delete turns that special color just like new turns a special color. So new, you explicitly ask for it, you use it, whatever you're going to do with it. When you're done with it, you tell the system you're done with it, delete it. But what you're doing, think of it this way, you're passing in the value of variable P and telling the system, I'm done with the storage that lives there. You're not done with variable P, you're done with the storage that lives in variable P, which in this case is hexadecimal F014. So that delete statement does this. One more thing. I know this is a lot and I'm sorry. I don't know how to make it a little because it is a lot. After you delete P, here's the situation. We've got a ridiculously messed up picture, but we also have a dangerous picture. Even though that storage got returned to the system, we're no longer using it, variable P itself still has the address of where that little ghost of a variable lives in memory. That memory no longer belongs to our program. We can't use it anymore because we said we're done with it and we gave it back. But P still knows where it lived. Doesn't live there anymore, it's not alive. But P still knows where it was. So a convention, a very strongly held convention, is after you do delete P, set P equal to 0. Why? Convention, convention, convention. By convention, a pointer variable that points at something is allowed to have a non-zero value. Unless it points at something valid that your program is allowed to use, a pointer variable should always have value 0. So even before I set it equal to the address of my counter, it would have been good to initialize it to 0. I've had so much trouble getting this video to record, I'm not going to go back and try to do it again now. This is actually, I think, iteration number 4, just on video AA. And those are my problems, not yours. After you delete what's pointed at, after you delete the storage that P points at, it's always a good idea to set P to 0. So now I can test. If I want to know if P still points at some valid memory address that I could use, I just do a quick if test. If P is not equal to 0. If I'm following my own convention here, if P is not equal to 0, then the address that it holds must be valid for me to use. It must be something that's been claimed for my program. If P is not non-zero, if P is 0, then it doesn't point at anything. I'll just have to let that go to voicemail. Actually, that's about it, I think, for this. If you absorb all that, then kudos. And if you didn't, then let's talk. Bring this up in Zoom sessions, either office hours or the class meeting, but I'm going to let that sit right now. I'll see you guys online and struggle with this. I know I struggled with this the first time I ever saw this stuff, but just watch it more than once, write down your questions, come up with hypotheticals and ask me about it, and I'll see you online.